How do you measure something so enormous that it includes everything? Time, space, and even light itself. If the universe had a birthday, what clues would tell us how many candles to put on its cake? The quest to measure the age of the universe is a story of light's journey across unimaginable distances, and the cosmic code that journey contains. Consider these words. Lift up your eyes on high and see who created these. He who brings out their host by number, calling them all by name. That vision from ancient scripture imagines looking up at the stars and asking big questions, not just about their names, but about their origins and how long they've shined. What does it really mean to look at a star and see the past? The light streaming from even the closest stars takes years to reach us. Light leaving our nearest neighbor, Proxima Centauri, spends over 4 years in the blackness of space before it's captured by our eyes or telescopes. That star could have vanished years ago, and we'd still see it twinkling, its light a ghost of the past. This delay is more than a curiosity. It's a built-in time machine. Every photon, every tiny particle of light has a timestamp. When we detect it, we're peering backward across space-time. The farther away a galaxy lies, the older the light we see. But how much older? How do we turn this poetic sense of gazing back into a ruler for the universe itself? One answer comes from something we all know. When something moves away from us, the sound or light it emits stretches out. Imagine an ambulance racing away, its siren dropping in pitch as the waves are stretched. With light, we call this phenomenon redshift. As distant galaxies speed away, their light shifts toward the red end of the spectrum, like turning down the color temperature on a cosmic lamp. In 1929, astronomers saw that the farther a galaxy is, the faster it moves away. This observation wasn't just a matter of speed. It revealed that the fabric of space itself is expanding. The universe, it turns out, isn't like dots moving through a still space, but like spots painted on a balloon that stretches larger and larger, carrying everything with it. Pause with that image. A universe where everything is receding, not from one center, but from every point, all at once. Where do you measure from in a cosmos with no edge and no center? It's one of the most mind-bending concepts in cosmology. The answer lies in the light itself, which encodes the history of that expansion. Redshift tells us how much the universe has stretched since the light left its source. If you look at a distant galaxy and see its light has doubled in wavelength, then space has doubled in size since that light began its journey. Here is a passage from ancient poetry. He has made everything beautiful in its time. Also, he has put eternity into man's heart, yet so that he cannot find out what God has done from the beginning to the end. This speaks to the tension between our urge to know and the scale that thwarts us. But with Redshift, humanity built a bridge between what happened at the beginning and what we see today. By measuring how redshift accumulates with distance and how those speeds relate to how far off these galaxies are, we can extrapolate backward. If everything is moving away now, we can imagine all objects once existed in one impossibly dense point. That's the moment we call the Big Bang. Not an explosion, but the beginning of cosmic expansion. To turn this idea into an actual measurement, an age in years, astronomers need more than just a sense of stretching. They need a rate. How fast is the universe currently expanding? This is known as the Hubble constant. It tells you, in effect, how many kilometers each million light-years expands per second. Suppose the universe were expanding at a fixed rate. You could simply run the cosmic movie backward, tracing everything back until all the galaxies pile up at the beginning. The time this would take is called the Hubble time. For decades, refining this calculation was one of astronomy's central quests. Because small errors echo across billions of years, scientists used exploding stars called supernovae as cosmic yardsticks, tracking their brightness and redshift to map the expansion in real time. They also measured the properties of the oldest star clusters and the composition of elements in ancient gas clouds, seeking independent clues. But perhaps the most astonishing window into the universe's age is older than the oldest star. It's the afterglow of the Big Bang itself. This cosmic microwave background is a thin static radiating in all directions, a faint glow imprinted when the universe was just 380,000 years old. A baby picture showing the cosmos before any stars or galaxies existed. Every photon in this afterglow has been stretched by the expansion of space, redshifted for over 13 billion years. By studying the precise pattern of tiny temperature fluctuations in this background, ripples caused by sound waves freezing into place, cosmologists deduced the universe's age with breathtaking precision. Today, the best estimates place the age of the universe at 13.8 billion years. 13.8 billion years. It's a number almost too vast to grasp. That age is written in the faintest patterns of light. Light that left its source before even our solar system was born, and only now reaches our detectors on Earth. It's remarkable to consider. Everything you see is, in a sense, a story from the past. The table in front of you reflects light that left a fraction of a second ago. The moon, about a second and a half. The sun, 8 minutes. Proxima Centauri, 4 years. The most distant galaxies visible, over 13 billion years. Looking out, we can't help but look back. And yet, these stories of light, scrupulously measured and traced, reveal not just the age of the universe, but a sense of our own place in its history. We are, as the poet once wrote, made of star stuff. The atoms in your body trace their heritage through the fires of stars, born and died long before Earth formed. Listen to these words from a philosopher. Time is a moving image of eternity, which moves according to number, but eternity remains ever at rest. In studying the universe's age, science turns eternity into something we can label and count, even as the deeper mystery remains. It's worth reflecting on the methods used and the questions still open. Measuring with light seems clean and absolute, but light's journey is subtly affected by the bending of space, the expansion rate changing over time, the invisible pulls of dark energy and dark matter. Each measurement has its uncertainty, its assumptions. Even today, astronomers debate. When local measurements of the Hubble constant disagree with distant cosmic measurements, are we seeing a new property of the universe, or just another calibration error? The universe may be stranger than our current models admit. Still, the thread of certainty is this. Light is an honest witness. It travels at a fixed speed, and its changes are traceable. When we measure the age of the universe with light, we are not just calculating a number. We are translating the silent journeys of ancient photons into an epic timescale, forging a timeline from the moment of origin to the present. The next time you gaze up at the twinkling stars, remember, you are not just seeing points of light. You're receiving messages sent millions or billions of years ago. And you, standing on a small planet, are a participant in the universe's long and ongoing story, a story written in the language of light and measured on the scale of eternity.